Let's talk about efficiency. Different efficiencies can be defined. Let's start with the maximum theoretical efficiency, the Carnot efficiency, which is given by the equation on the right and only uses absolute temperatures and temperature differences between the hot and the cold reservoir. We can use this to, let's say, benchmark the efficiency that we achieve in our system and take a look at how close we can get to this Carnot efficiency. More practical, we take a look at the COP, the coefficient of performance, or EER, energy efficiency ratio, basically the same things for heating, COP, and cooling EER operation, defined according to the norm, the EN 14511, and this gives the steady state, the efficiency at steady state conditions for different source and sink temperatures. So you put the heat pump in a climate chamber, you turn it on, you have a certain temperature on the source and a certain temperature on the sink. You wait until everything is steady state, and then you measure the amount of energy that you put in, the amount of energy that you take out, and the ratio between those two gives you the efficiency at those operating conditions. Then we can have the seasonal COP and seasonal EER, coefficient of performance energy efficiency ratio, which gives the seasonal efficiency adjusted for part load conditions according to the EN 14825. And this means that we look at different temperature regions, Northern, Middle European and South European, and look at how the part load conditions are distributed over the ambient temperatures and adjust for those. This still does not give us the real efficiency, the SPF, the seasonal performance factor, because it does not consider the relative amounts of energy between heating operation, domestic hot water production, and active or passive cooling operation. So the seasonal performance factor actually does this and can either be calculated or measured in the building and provide us with a real efficiency of the system. The main thing about efficiency is the difference between the cold, the evaporator, and the hot, the condenser side, the difference between the source and the sink. In the graph, we can see that at a low condensing temperature, 25 or 30 degrees, and a high evaporator temperature, 7 or 10 degrees, we have a very high efficiency of the heat pump, somewhere between 6 and 7. Hot water production for domestic hot water at 55 degrees and a low temperature on the source side, for instance, at the end of the winter in year 30, 0 degrees or -2 degrees, we have a low efficiency around 2.9 or 2.7. Another use of the system with passive cooling or passive heating even, where the heat pump is not used, we only use the circulation pump, and then obviously we get a very high efficiency because the energy used by the circulation pump is relatively low. Note that air source heat pumps may require defrosting cycles, and that has a big effect on the efficiency of an air source heat pump. Now, looking at an example with different source temperatures and different user temperatures, B stands for the ground, for the bodem in Dutch, and W stands for water. So we have B0, W35, the ground is 0, and the water side is 35. The Carnot efficiency that we expect is 8.8. The actual efficiency, the COP of a heat pump, would be around 4.8, and the Carnot efficiency, or the achievement of Carnot efficiency, is about 55%. So we have a little bit more than half of the maximum available, maximum attainable efficiency. Taking a look at other conditions, for instance, we are creating domestic hot water at 55 degrees and the ground is still 0. We have a COP or EER of 2.9, and the Carnot efficiency that we achieve is 48%. In passive cooling, with the ground at 0 and emission side at 20 degrees, the Carnot efficiency would be 25 and the actual COP would be 20. So we have an 80% approach of the Carnot efficiency. So what we can see in general is with the heat pump in operation, we can get to about 50% of Carnot efficiency. And in passive mode, we can go up to 80% of Carnot efficiency, which is pretty good. Now, there are different efficiency demarcations. We've talked about the compressor. We've talked about the ground source pump, but obviously we can also have a pump on the user side. We can have additional electrical heating and all kinds of other items in the system, energy users in the system. There was a nice project of the European Union, the EU CPMO project that actually defined different system boundaries for calculation of efficiency. And in this graph, for instance, you can see the COP1, only the compressor energy is accounted for, COP1 or SPF1, and COP2 or SPF2, the compressor energy, and the source pump energy is considered. And this is what we are usually interested in from the ground source energy perspective. So we come to some final remarks and key points. Clearly, the efficiency depends on the temperature difference between the source and the sink. The smaller the temperature difference, the higher the efficiency. Another point is that we would like to design for a small capacity, use a small capacity heat pump to deliver as much of energy as possible, because we save energy. We do not save on capacity. In practice, the part load behavior of the system is very important, and this means that we would like to use either a frequency-controlled compressor or a multi-compressor system to match the capacity of the heat pump system with the actual demand side on the building. We would like to prevent also a high number of cyclings of the compressor start-stops. If the compressor size is too big for the load, it will start-stop very often, and this will result in low efficiency, but also it will wear out the compressor and cause faults. And finally, on the building side, what's very important is to ensure a low return temperature in heating and a high return temperature in cooling, so that the heat pump system can heat the fluid and cool the fluid in an efficient way.